Hello, everyone. We are very glad to introduce our new paper, Gs-Livm, Real-Time Photorealistic LiDAR Inertial Visual Mapping with Gaussian Splatting. This paper presents a real-time, photorealistic mapping framework utilizing 3D Gaussian splatting, specifically designed for large-scale, unbounded outdoor environments. The ability to operate in real time is a key feature of this work. The accompanying illustration depicts the mapping procedure, demonstrating our capability for real-time map expansion and the rapid completion of high-quality photorealistic renderings. Furthermore, we have evaluated various types of LiDAR systems, including solid-state LiDAR and multi-line spinning LiDAR, to ensure the framework's versatility and effectiveness across different sensing technologies. This overview presents the two main threads developed in our framework. The first thread is the tracking thread, which utilizes a typical LiDAR inertial visual fusion algorithm to estimate an accurate and robust camera pose, allowing for the transformation of the colored point cloud into the world coordinate system. The second thread focuses on Gaussian splatting for dense mapping and map expansion. Our dense mapping primarily utilizes the observed LiDAR point cloud to initialize the Gaussian splatting point cloud. Beginning with a global hash-colored map, we first develop a voxel-level Gaussian process to address the sparsity and uneven distribution of the observed point cloud. In our implementation, we create a CUDA-based program to accelerate computation, which is essential for real-time map expansion. Simultaneously, the camera poses will also be input into the dense mapping module. Please note that the variance from the voxel GPR module will be used to initialize the scale and rotation parameters of the 3D Gaussians. Additionally, the image captured at this timestamp will be reprojected to obtain the color information for the 3D Gaussians. Subsequently, the newly added point cloud will be updated in the dense 3D Gaussian splatting map for iterative optimization. In the optimization thread, we rasterize the RGB color image, the depth image, and the silhouette image. In the loss function, we utilize L1 loss and SSM loss between the color image and the ground truth image, delta depth loss between two adjacent frames, and structural similarity loss between the 3D Gaussians and the originally observed point cloud to supervise the training of the dense mapping. This demonstrates the voxel GPR module, where we predict a uniform distribution point cloud to fit the original point cloud. We assume that these two variables share the same distribution, utilizing Gaussian processes for point cloud modeling. This is the ablation experiment for the voxel GPR module. On the left-hand side, when point clouds are directly inputted, the 3D Gaussians tend to obscure each other, resulting in insufficient supervisory information for each individual 3D Gaussian. In contrast, our method samples the distribution, leading to improved quality compared to the previous approach. This is the 3D Gaussian fast initialization algorithm. For each grid, we divide it into n\times n subgrids. Then, for each subgrid, we use the following equation to estimate a sphere, resulting in each grid containing n\times n spheres. These spheres will then be integrated into the 3D Gaussian map. This illustrates our module, which accelerates the optimization of 3D Gaussians. More ablation experiments can be found in our paper for further reference. We validate our algorithm on several datasets that include different types of LiDAR data. Compared to other methods, our approach achieves the best rendering quality. It is important to note that our framework is the only algorithm capable of running on a single 8 GB memory GPU and successfully completing reconstruction across all sequences. This demonstrates that our algorithm is the most efficient. Below are the rendering results across different datasets. This is the time analysis of our algorithm. The standard performance of our algorithm is close to 100 milliseconds. On the left-hand side, we can see that we can easily achieve real-time performance within 2 minutes. On the right-hand side, our algorithm demonstrates competitive time consumption. The box plots illustrate the time consumption across different modules of our algorithm. These two videos showcase the reconstruction models using different types of LiDAR data. As we can see, the quality of the reconstruction is impressive. Most importantly, these results are generated in real time. Thank you for watching. If you have any further questions, please refer to our paper and code.